Okay, so in our constant velocity lab that you guys did and updated your data to the discussion board, you basically came out with graphs that looked something like this. Not perfect, but something like that, where you had position on the y-axis, time on the x-axis, making sure that you label these. Whether it's in meters or centimeters, it doesn't matter. If our line is a straight line like that, we can get a lot of information out of it, and we can use it to talk about whether the velocity is constant or not, to determine what its speed is, as well as to find out some other information that will be useful later in terms of the equations that we're going to look at. So while I'm going to come back and forth to this screen, I also want to look at your particular data. So this is Lucas's data. You can see that he has graphed on here distance in centimeters on the y-axis, time in seconds on the x-axis. And over here on the left, he has an equation of the line right here. And that equation of the line is important because it tells us that if we do a best fit line between our points, that's what the blue line here shows, then it does in fact make a straight line. When we are doing data points and when we are graphing them, we don't want to connect them dot to dot. We want to draw the best fit line through them or to do a regression line through them. And Lucas figured out that his line is y equals 9.5x. So if we go back to my other paper for a moment, and we use that as an equation, y is equal to 9.5x. One of the things that we want to make sure we do is we want to make sure that we put this into units that are specific to our experiment. So rather than saying y equals 9.5x, we should say that distance in meters, oh, yours was in centimeters, sorry, is equal to 9.5 times time in seconds. Which means that for every centimeter we increase our distance, then we are going to know how long it takes us to do that by multiplying our time by 9.5, or vice versa. If we know that we've gone 1 second, then that means we should be 9.5 centimeters from the origin. So this 9.5 here, number 1 represents the slope of our line, which, remember, the slope is the change in y over the change in x, which in this case is the change in position over the change in time, which, as I said on the other video that I made recently, this is a velocity. The reason it's a velocity and not a speed is because we can have a negative slope as well, and therefore, because this is positive, it is telling us that it is a positive slope and it's in the positive direction. The first equation we came up with here is that delta x over delta t is equal to velocity. Remember that delta x is our change in x's. So delta x is x2 minus x1 over your time, and that is your speed. Sometimes we have to think about this as an average velocity or an average speed because, like in this case, there was a little bit of a blip in the middle. So we often think about this in terms of averages instead. So we can keep it written as a fraction, or we can write it that delta x is equal to vt. And if we change this from being x2 minus x1 to being the final position minus the initial position, we then get x final minus the original position is equal to vt. which again means that our final position is equal to our velocity times time plus our initial position. In Lucas's case, that comes back to, again, this equation here. So for Lucas's experiment, then our final position is equal to 9.5 times our time plus our initial position, which we know for his was 0. So our 9.5 is in fact our velocity, which means it should have units of centimeters per second. If we take a look now at Amanda's data, Amanda had this data listed, and her distance is in meters, her time is in seconds. She too has a little blip here at about 3 seconds, so I don't know what happened to your vehicles at 3 seconds, but that's okay. Now, when you first graph on Desmos and it gives you this line, it doesn't connect the dot, but we can say that we don't want that, and instead we can put a line of regression on it, is what they call the best fit line. And to do that, let me get rid of that too. You simply click up here to the plus, and you say, I want to add an expression, and that gives us the option to add it up here. We know that the equation of a straight line is y equals mx plus b, so I want to tell the computer to do that. So what I can do is I can say I want my y1, which is my y-axis, to be equal to my slope times my x1. And then notice that it gives me a bit of information here. Number one, it gives me the r-squared value of 0.947. R-squared value tells me how close my data actually comes to this straight line, to this best fit line. You never want to have a best fit line that is under 0.9 because that means it's a very bad fit. This is not a percentage. It's a different type of calculation here. The closer you are to 1, the better. So 0.947 isn't bad, but it's not great. And you can see that over here. Whoops, sorry, I didn't mean to move that. You can see that over here at the 3-second mark where it's quite a bit away from the best fit line. So this m, though, they also tell you what the slope is. The slope in this case is 0.27185. Well, our data only went to the second and third decimal point, so we aren't going to keep going here. We're going to round this to be 0.27. So for Amanda's graph, her equation was y is equal to 0.27x. And again, we're going to switch it to the other units. So x in meters this time is equal to 0.27 time in seconds. If we go along the same thought process as we did with Lucas, then we can say automatically that this 0.27 means that her vehicle was traveling at 0.27 meters per second. If we want to change this into centimeters per second so we can compare it to Lucas's, remember that there are 100 centimeters in a meter, so we would have to multiply this by 100, which means that her car was going 27 centimeters per second. That's Annabelle's velocity, and Lucas's velocity was 9.5, I think. Where are we? Yep, 9.5. So almost 3 times as fast. Does it matter that your cars were going at different speeds? No, it really doesn't. The important thing to get out of this is what we can understand from the graphs and what they show us. So when we have a graph similar to what you guys were able to get to, where we have x and t, straight line, There are some things that we can say about this graph. Number one thing that we can say about this graph is that because it's a straight line, distance and time are directly proportional. Directly proportional means that they start at the origin, and then as one goes up, the other goes up and they go up together at a constant rate. So the data changes or the data increases at a constant rate. As we've said over here now a few times, the slope represents the rate of change or the speed of the object. Whoops. Rate of change or speed of the object. The y-intercept, which you may have had a y-intercept on your graph if you hadn't started with a data point of 0, 0, which technically, unless you actually took that piece of data, you should have ignored in your graph. But the y-intercept represents the starting position. So when we are looking at this particular lab, the conclusions you should have come up with are these three, along with the equation that we used on the last page, which shows then that the generalized equation is that delta x is equal to vt, and that the rate of change is equal to the velocity times the time. This generalized equation is, like I said the other day, one of our first kinematics equations. One of the other things that we should talk about briefly here is the fact that there was some error, and that error is not huge. It was based on the fact that you both knew that the cars you were using were not exactly constant velocity vehicles, but you did the best you could to simulate a situation where they would in fact be different. So summing up for this constant velocity lab, these are the things that you should have taken from it, and keeping this in mind is going to be really important because our next experiment, which you should have the kits for, we will do a similar experiment, but we are not going to want to get this sort of line. Because we can figure out what the slope of the line is and what the speed of the object is, I could ask you, but I'm not going to then take this information and make it into a velocity time graph. And you could do that because we have this over here. So Lucas's speed is 9.5 centimeters per second. So if I make each of my lines here say worth 1.5, which isn't a great idea, but I made it tiny, so 9 is here, so that would be 10.5 there, so 9.5 would be about here. Then I could say, all right, velocity time graph, there it is. And Annabelle's would look the same, hers just would be significantly higher than that. So we can in fact go from having a position time graph to a velocity time graph with our lab and with our data here for the lab. But because I screwed up on thinking that your graphs weren't showing a constant velocity, I don't know what I was thinking they were showing. You do not have to do the lab report for this. We're just going to skip that completely, and we will start our acceleration lab next week after we have gotten finished up with constant velocity. Hope this was useful, and I will see you later. Bye.